Great. Yeah, thank you very much for having me. My name is Anna-Christina Eilers. I'm just from down the road from MIT, and I'm going to talk very briefly today about a new idea I'm currently excited about, which is to create tomographic maps by means of the Lyman alpha forest of the emission of high-redshift quasars. This is not working. Okay, there we go. For those of you who have just been to colloquium, sorry, this is slightly repetitive, but one of the questions that I'm particularly interested in is the question of how do supermassive black holes form and grow, especially at early cosmic times, where we know we have these billion solar mass black holes already at a time when the universe is still very, very young, like less than a giga-year old. And so if you just naively trace back their growth history to the beginning of our universe, you can maybe barely explain the growth if you invoke very massive initial seeds. But for various reasons that that has been laid out by many people, this is likely not the complete picture. There's many more other things that are likely going on that prevent us from just simply tracing back the growth history to the beginning of our universe. And just a few ideas that I laid out earlier of what could be going on is there could be, or what could make this picture more complicated, is that there could be obscure dust-enshrouded black hole growth phases where we maybe not see these black holes, these early quasars, or we could have maybe radiatively inefficient accretion rates that would make these curves much steeper. There's many other solutions that have been proposed in the literature, but here's just two of them. And this is not in any way anything new. This is an old problem, several decades old, I think now. And people have been trying to solve this for a very long time, approaching it from many different angles. And so what I'm trying to do is figure out whether there is a new observational method, how we can maybe, possibly disentangle these two scenarios. And so the work is motivated by this work that we did with the Eiger team, where we looked at high-redshift quasar fields with JWST. This is the most luminous high-redshift quasar that we know. And we looked at this not only in imaging, but we also put the GRISM in the light path. So we get spectra for every object here in the sky. And then we look at this emission line doublet here in particular, which is from doubly ionized oxygen. And that allows us to determine the redshifts of all of the galaxies in the high-redshift universe around the redshift of the quasar. And so I've been talking a lot about all the galaxies that are at the same distance between us and the quasar. We can use those to study the clustering properties of the quasar. What I want to do now is focus on all the galaxies that are actually in the background of the galaxy, of the quasar from our point of view, and how we can maybe use this to understand more about the growth of the quasar. So if you imagine we could look at this from the side, which we're going to do now. So we have the quasar here as this yellow blob, and then we have the spectrum here. You can nicely see how strongly clustered those galaxies are in redshift space. We have this strong overdensity around the quasar. There's some more here. But then we also have a lot of very bright galaxies actually in the background of the quasar. And those usually we didn't know we had them. We didn't know they existed. But there's very few efforts that are so far going into leveraging those galaxies. And so what I would like to do is, this is just showing the same thing again, basically. The observers here on the left, here's the quasar, and everything that is in red, the galaxies in the background. And what we're trying to understand is what part of the universe has been carved out, has been ionized by the quasar's radiation. We're talking about redshift 6 here, so everything, the intergalactic gas is fairly neutral, but because the quasar ionizes its surroundings, it caves out that bubble of ionized gas around it. And the longer the quasar shines and ionizes its surrounding, the longer the black hole grows, the larger is this bubble of ionized gas that is creating in the otherwise neutral IGM. And so that lowers the optical depth, and we can actually see flux transmission going through the universe, being transmitted to our telescopes on Earth from those background galaxy sidelines. And so that motivated us to write the cycle 2 and also cycle 3 proposal that we called Masquerade. The acronym changed many times. At the moment, it stands for Maps of a Quasar's Extended Radiative Emission. And so it's using the near-spec MSA to get galaxies in the background and in the environment of the quasar. And it's about 20 hours per field, so fairly deep observations. And we get 2 quasars. And so the first science goal is really to try to map out where the quasar has ionized its surroundings, where the radiation has been able to reach. And the second goal is very related to that, namely to understand what are the sources of reionization, because these ionized bubbles in the high-redshift universe are excellent laboratories to study the ionizing emission of high-redshift galaxies that would otherwise be attenuated by the IGM. But now we have the ionized gas there, and so we can really understand what is the ionizing emission of those galaxies. And so for 2 reasons, we want to map out where this quasar has been ionized, its surroundings, to understand the morphology of it, the extent of it, but then also to figure out which galaxies lie in these ionized regions to understand what their emission is. And so I'm going to focus on the first thing now, and this is a very simple, cartoonish idea of what we're trying to do. But basically, if the quasar's lifetimes are very short, the quasar has been shining only for a short amount of time, maybe with radiatively inefficient accretion, we should see only a small ionized region around the quasar, whereas if it has been shining for much longer, but maybe obscuration effects play a role, we should say much larger ionized regions, but maybe inhomogeneously ionized. And this doesn't have to be in this biconical shape, it's just for illustration purposes. And that's something that we think we can actually measure in the galaxy spectra of these background quasar sightlines. So we got data already for one of the quasars, unfortunately the fainter one, so it's not the best object out of the 2 that we proposed for. The other one is coming in December. And we just finished the data reduction, so what I'm going to show you next is very, very, very preliminary. Hopefully we can improve on this, but what we did is just stack all the galaxies as a simple thing at the redshift of the quasar, where we would expect to see transmission if we can really probe this ionized region around the quasar. And we can argue about how many sigma this is or whether it's a detection, but it is at least promising to see that there might be some signal in the stack of, in this case, only 6 objects. This thing here is Lyman alpha from some of the background galaxies. And what's sort of interesting to see, and again, this is very preliminary, that's also why the plots don't look super pretty right now, but here's the quasar. These are all the background sightlines that we were able to put on MSA slits, and all the ones where we do think there are maybe some transmission flux spikes, they sort of lie in, or at least most of them lie in like the upper direction, suggesting that possibly the ionized region is actually fairly extended, but maybe there's some obscuration effects because none of those objects here that are as equally bright than those show any transmission. And then because our team includes a lot of people who care about galaxies, I'm also made a stack of all the galaxies because we have very deep MSA spectra now for a large sample of these galaxies. And this is just a stack of the brightest of them, not actually all of them, just the brightest ones. And you can see, I think, a few nice things. You can probably see a damping wing here. There's a lot of these lines, emission lines that people get excited about, like helium-2, for instance. And 4 has been used to argue that there's an AGN, maybe in GNC 11. Now it looks like we can probably see it in the stack, although we have to see how many of those galaxies drive this. And then we also see absorption, significant absorption in C+ and silicon-4 here. And so, yeah, I just want to finish really by saying that the near-cam grism is fantastic. If you haven't used it and want to write proposals, use the near-cam grism. You get redshifts, a spectra for really every object in the sky. It's a bit of a tedious way to reduce the data, but it works by now really, really well. And so we're using this to find all these high redshift galaxies. And at the moment, we're trying to get spectra of all of them at lower wavelengths to really understand whether we can map out the 3D emission, tomographically map the 3D emission of those high redshift quasars. Thank you very much. In the galaxies? I don't think so, and also they're not quite as high. Like, well, we see already some of those lines, right, in the redshift 11, redshift 12 galaxies. Here we're talking about redshift 6 to 7, so we have a few hundred more million years to do this.
Any other questions? It's a great idea, this tomography thing. So how far away are those other galaxies with transmission? Is it like 10 megaparsecs?
Yeah, so this is our whole field of view. So it's only in the transverse direction,
Okay.
it's actually only like about 1.5 to 2, depending on the proper megaparsec. And then
How far out do you expect this quasar ionization to extend?
yeah, so it drops off, right? But we do, so we basically do expect it to almost ionize the whole field of view if the lifetimes are long enough. And so it's only for short lifetimes that we would expect the ones at the edge not to be ionized, really. So,
Yeah, thank you.
Any other questions? Go ahead.
So I'm interested about what the lifetime would do.
Yeah, good question. So it depends on the light travel time only, right? So it's only like how long does it take the quasar to travel? And I don't have the numbers, about 10 to the 6 years or something. So you can see it in here, right? So this is, about 10 to the 6 years, you reach the edge of our field of view. And that's set just by our field of view from the observations, really.
So you're saying that everything you see is already like most of the region?
Yeah, so the ones, let me go to the, sorry, I'm jumping around here. Let me go to this. So for this particular quasar, we actually get a lifetime estimate from the proximity zone. And if that's correct, which it doesn't have to be, but if it is correct, then we would actually expect a very young lifetime. And so this is this red line here. And so you wouldn't expect anything out at the edge of the field to be ionized. But if you have like these larger lifetimes, maybe with obscuration, you would expect that all of the lines of sight could be ionized. And the same actually for the other one as well. Thank you.
Does it work? Just a sec. Okay. Great. Okay. Hello, everyone. So my name is Gilad. I'm a PhD student at the Weizmann Institute. And I'm going to talk today about the non-thermal emission that follows GW170817. It relates to some of the work we've been doing in the Weizmann Institute. And I hope you find it interesting. OK, so GW170817 is quite famous. So basically, it's a compact neutron star that was merged 7 years ago. Hopefully, we're all familiar with that. So when we're discussing compact objects merger, or at least the electromagnetic signal that relates to compact objects merger, typically we're discussing binary neutron star mergers and black hole neutron star mergers, because we need a significant mass ejection if we're discussing an electromagnetic signal. When these two compact objects are close enough, they're going to lose energy due to gravitational waves. Eventually they're going to merge. So there are a few potential transients that are related to these kind of mergers. There's GRB, there's the Kilonova that we did observe from GW170817, and there's the non-thermal afterglow that I'm going to discuss here today. GW170817 was a great example because it provided us with both, or with gamma ray emission, with Kilonova thermal emission, and with the non-thermal emission that we're going to discuss. So we're going to focus on that. So what really happens when such compact objects merge? So when they lose the energy to gravitational waves, they're going to eject mass in a to the mildly relativistic ejecta. This is denoted here in blue. It will be quasi-spherical, and it is related to the shocks that has been created due to the collision between the two compact objects and due to tidal forces. There's also the highly relativistic outflow that is ejected from the poles. Usually it is called as a relativistic jet, so denoted here in red. Both of these components it's simply an outflow that propagates into the interstellar medium. It will create a collisionless shock that accelerates electrons to highly relativistic velocities. It also creates magnetic fields. So when you have highly relativistic electrons in magnetic fields, you're going to see synchrotron radiation. So basically, if you'll be able to model this kind of synchrotron radiation, you'll be able to say something about this the outflow structure we are interested in. Basically, there are many open questions regarding this type of outflows. As you all know, probably these outflows can create very heavy elements, and this is a very interesting thing to research. And currently, it is unknown what would be this outflow structure, its geometry, its velocities. OK, so this is the thing we're trying to understand. OK, let's go to GW170817 non-thermal emission. So this is the light curve. Typically, it was observed from radio to X-ray. All of the observations here, which both the radio and the Hubble Space Telescope optical observations and the Chandra observations, all of them are normalized to 3 gigahertz to radio observation using the synchrotron spectrum. So all of them sits on the same light curve. So we got a typical number for the synchrotron spectrum. It is exactly what we expect. F naught goes like nu to the power of minus almost 0.6. So the light curve, as you can see, has like a moderate rise up until 150 days, and then a very steep decline up until 1,000 days. These were our last observations. So typically, when you try to model this stuff, you would think about this ultra-relativistic jet that propagates in the polar axis. And this is how you usually model GRBs afterglow. OK, so GW170817 had another very unique property. It was observed to have a superluminal motion. It means it has a localization on the sky by the Hubble Space Telescope after 8 days after the merger. This is due to the Kilonova thermal emission that was seen in the first week or so. But 75 days later, and 206 and 230 days later, it was localized by the radio observations. So on the sky, it moved superluminally, which basically means there's a relativistic component that propagates in some significant viewing angle towards us. So it's simply a relativistic effect. Typically, when you just use point source approximation, trying to model this kind of movement on the sky, you would have like a Lorentz factor of around 5, and viewing angle which is between 15 to 30 degrees. Okay, so this is the parameter space we're looking at. So we know we have a relativistic outflow. We know it moved in some considerable viewing angle towards us. So what the natural thing to do is just use simplistic GRB afterglow modeling. So this is called the top hat jet model. It has like a very narrow angle of ultra-relativistic material. The energy per solid angle along this narrow cone is constant. And okay, so this is what you usually use. But if you use it, to try to use it for GW17 or 17, you encounter a problem because if you observe in some significant viewing of such a component, you would see a very steep rise in your light curve. Obviously, this is inconsistent with what we observe in the light curve, so this typical modeling cannot work. Okay, so the first problem, what did people do? Okay, there's no problem. There's this top hat ultra-relativistic jet still in the middle there. But now there's also an angular structure, like in its surrounding. You have some free function of the energy angular profile as a function of theta. It can be typically either a power law or Gaussian. So many different groups use this type of modeling to try to fit for GW17 non-thermal observations, 17 or 17. So now when you observe such an outflow off-axis, there's the unveiling of initially hidden angular sections due to relativistic beaming. So for example, if we're talking about this part of the outflow here, you wouldn't be able to see it as an observer here due to relativistic beaming until it decelerates enough. So as different parts decelerate, you can see further and further into your angular structure. This creates the very moderate rise in the light curve. Okay, so this was a good way to solve this moderate rise. Problem was that, the challenges with this kind of modeling is as follows. When you actually take this kind of structure and goes to full 2D relativistic hydrodynamic calculations, you get a decline in your light curve, which is too steep compared to what we see from GW17 with 17. Now, it might be possible that a more moderate profile here can create a decline, but no such simulations that can recreate this decline are out yet. So this is the first challenge. The second challenge is that when you use this semi-analytic fits try to approximate what would we look like, what the signal from such an outflow would look like, they can't fit both the light curve and the centroid motion together at the same time. So this is another challenge. So it seems like there are challenges using this type of modeling to fit all of the observations of GW17 with 17. Okay, we suggest a different option. So on the right-hand side, you can see the typical modeling that is being used today. On the left-hand side, you can see our new option. So we consider a conical stratified outflow. What does it mean? It means we consider an outflow which has a radial structure. It means that the low-density, high-velocity layers are up front, and the high-density, low-velocity layers are at the back. We consider a much lower Lorentz factor and a wider viewing angle. So first point we want to emphasize that the shallow rise in this scenario is due to a completely different mechanism. The inner layers keep on converting kinetic energy into internal energy of the shock. So they keep on pushing energy from behind. This is why you can see this very shallow rise. And due to the wider angle and the lower Lorentz factor, the decline is not as steep. So we can also create both the rise and the decline with such modeling. Now, if you think about it, obviously, when you eject material in the polar axis, obviously such a radial structure has to be created at some point, because the faster layer will be up front with the lower density, and the lower velocity will be at the back. So there has to be some kind of radial structure to this outflow. So it has a very clear physical motivation. Okay, so now it's a nice story. You can tell this story, but let's see what can you actually calculate. So first of all, we created a semi-analytic calculation that approximates what would be the observed light curve and centroid motion from such an outflow. In order to actually create semi-analytic calculations, you need to assume many things. So one of the assumptions we made is that the lateral expansion is negligible, which means that we can treat our outflow as a simple angular section of a sphere. This is a very this is an approximation, so we had to make sure it is actually correct. there's a good physical motivation to this approximation, because if you think about it, the inner layer keep on pushing momentum in the radial direction. So you expect the radial direction to be still dominate your outflow propagation. But it is simply an approximation. So we had to run full 2D relativistic hydrodynamic computations in order to validate this result. So you can see it here on the right-hand side. There's an initial cone, and it opens up very slowly. And okay, so let me go to the result. We had to use full 2D full 2D calculations. We found they fit actually very good the semi-analytic approximation, and this is how it looks like. So on the right-hand side, you can see the centroid motion from GW170817 with our full numeric computation that fits the data. On the left-hand side, you can see the same light curve from before. Again, this is the full numerical computation from the simulation. We used the semi-analytic calculation to fit the data, and then we ran the full 2D relativistic hydro calculation to actually make sure we are correct. Okay, so this is the first single component full numerical computation that fits all of GW170817 non-thermal emission. It has different conclusions regarding the outflow properties, velocities, and opening angles, so it should be considered in the future. I also had analytical modeling for the break frequencies, but we don't have time for this, so let me just conclude. So it's an alternative approach to fit all of the observations, all of the non-thermal observations from GW170817. It's a radially stratified, wide angle, and with a lower Lorentz factor outflow. It accounts for all of the observation. It has a different viewing angle dependence if you look at it from different viewing angle. So the structured jet scenario would have a different behavior from this outflow. So it provides us with a simple method for verifying which kind of outflows from future observations, which kind of outflows to distinguish between the two possibilities from future observations. And we also derived analytic expressions that relate to the synchrotron spectrum, but we don't have time for this, so thank you.
Thank you. So what fraction of the total mass of the system participates in this?
So we're talking about 2 neutron stars, so it's more than 2 solar mass. So this thing is a tiny fraction. It's less than 1,000th of solar mass.
Any other questions? Ramesh?
Very interesting model. In fact, I think the supernova ejecta have this kind of layered structure. The fastest guy goes out first.
Yeah, it is a natural explanation.
It's a very natural thing. So I was wondering, do you expect any reverse shock radiation? Because that fellow will be sensitive to this radial structure that you are involved.
So we actually calculate also the reverse shock emission. We found it to be quite negligible, few percent of the total emission, but it is a good point to make sure. Yeah. So in the semi-analytic calculation and both in the numerical computations, we calculate both forward and reverse shock emission.
Okay. But most of what we are seeing is
Forward
the forward shock.
Yeah, indeed.
I'm wondering if this sort of velocity structure tells you that the moment that material is launched has to be kind of impulsive rather than continuous, because if it's continuous, then you imagine sweeping up into a flow that gives you these sort of standard jet, right? And here, either temporally you would have to launch the fast stuff first and the slow stuff later. Or it could be all at once, and that gives it the velocity.
My answer will be divided to two.
Yeah.
First of all, we're still talking about Lorentz factors which are beyond 5. It means the velocity difference is negligible. All of these things propagate in 0.99 of the speed of light. Okay, so it's a very negligible velocity difference. The second point is that basically in the structured jet picture, you imagine a single layer with a very high Lorentz factor, so that when it propagates into the initial collision with the interstellar medium, almost immediately sweeps up all of the mass. So this is the thing you imagine. Now, we do know that the shock plasma has a Lorentz factor of about 5 from the centroid motion. Mm-hmm. So such a scenario in which you have a huge Lorentz factor and then you sweep up the mass that fast is not consistent with the full picture that we do observe. So there's a good reason to think that it would not sweep up all of the ejecta, all of the sufficient interstellar medium that fast. So it happens when you have lower Lorentz factor of outflows, and it could be the case.
Thank you very much. Do you have any more questions?
Great, thank you so much. Yeah, we'll go from non-thermal emission to thermal emission from neutron star mergers. So yeah, thank you so much for having me. My name is Jillian Rastinejad. I'm a final year PhD student at Northwestern, where I work with Wenfei Fong. So I'm really interested in the origins of the R process elements. So I like to just show the periodic table at the beginning of talks. So when I talk about the R process elements, I talk about elements synthesized through rapid neutron capture, nucleosynthesis. This is the process for forming about roughly 50% of the elements heavier than iron on the periodic table. And of course, thanks to a lot of work done by folks here at Harvard, and of course the amazing detection of GW 17817, we know that neutron star mergers are a prime source for this R process nucleosynthesis. So this was an absolutely amazing discovery, GW 17817, but we still have a lot of unknowns about the sites of R process nucleosynthesis in the universe. So in neutron star mergers, of course, we emit the thermal Kilonova emission. And so with 17817, we observed that in absolutely exquisite detail. But with only one event, we can't say too much about the diversity of kilonovae from an observational perspective. On the theoretical end, we have these amazing state-of-the-art models that are predicting diversity in kilonova light curves, the ejecta masses, composition for all sorts of, well, not all sorts of, but binary neutron star black hole, all different types of systems. We could also have different sorts of remnants. But of course, the observational constraints on these unique outcomes is really limited. The second unknown I'm going to talk about today is that recent simulations and indirect observational evidence suggests that there's a faster, relative to star formation, R process channel. And so right now, the favored candidates for that are rare types of supernovae. And then before I go on, I want to just emphasize that these events are really challenging to observe. We have really low rates. For the last decade or so, kilonovae are detected at a rate of about 1 per every 2 years. These events are very faint, and then they rapidly fade. We're talking about hour to day to week timescales. And so I like to just put up this fact, even 8-meter telescopes like Gemini, which I absolutely love, they only really get you to a horizon of about redshift 0.2, and you get about 2 to 3 epochs of imaging if you're lucky, weather behaves, et cetera. Okay. So in my research, I use gamma ray bursts to probe these sites of R process nuclear synthesis. So if you've learned about GRBs before, you know that we have these two broad classes separated by duration and hardness ratio. Short GRBs, which are generally connected to neutron star mergers and kilonovae. And then, of course, long gamma ray bursts, which are connected to the deaths of massive stars and supernovae. So I'm first going to think about how we can use long gamma ray bursts to address the sites of R process. Okay, so this is a figure from a paper by Daniel Siegel, where they find that the conditions for a collapsar supernovae are ripe such that you can form some amount of R process in the accretion disk surrounding the remnant black hole. And so this paper suggested that these collapsar supernovae are the best place to form this. And then, of course, collapsars are often used to explain GRB supernovae. So GRB supernovae are a prime candidate to look for this R process nucleosynthesis. And then we've also had a lot of recent work on the theoretical end that suggests that the presence of the jet may even increase the visibility of R process material. So, of course, getting R process emission lines detected is very difficult. You would have to take a spectrum of the supernovae at very late times. Of course, JWST is a great instrument to do this. Peter Blanchard has worked on this effort. But we have very few candidates and really no archival data to do this in. So instead, the approach that I've taken is to use colors. So your kilonovae are famously very red due to the high opacities of the lanthanide elements synthesized in that neutron-rich ejecta. And so you might expect, so these are just some light curves in the optical, and the infrared, and you can see that the model that's enriched with our process, this dashed line, becomes redder over time, which you can also see in these R minus H color light curves here. So this is, again, time and color. And you can see that compared to the R process-free model, and depending on the amount of mixing between the R process ejecta and the outer nickel-56 ejecta, you get this color change over time. So this is what we searched for. We collected late-time optical near-IR observations of 4 historical GRB supernovae. I got to reduce some HST data from back in 2003. That was quite fun. And so we got a lot of these late-time light curves. So I'm just going to kind of skip to the conclusions. So these are some grids for 3 of the GRB supernovae in our sample. Here we have the R process mass and then the amount that it's mixed into the ejecta. So higher numbers on the y-axis are greater degrees of mixing. And then that's just the chi-squared fit to the different models. And so we kind of conclude that it's inconclusive. So we have some models that could match the data. We're certainly able to rule out high amounts of R process and high amounts of mixing. But even in these favored candidates, it's inconclusive at the moment if they can produce the R process. But we use this study as motivation, and so I have an active HST and Gemini program to get observations that are really tailored to these models. Okay, on to the second part of my talk, which we'll think more about neutron star mergers. So this is already giving away a bit of a spoiler to the next slide, but I'm just gonna bring up this event quite quickly. So back in 2021, I led a team that followed up this gamma ray burst that for all intents and purposes looks like your typical long duration GRB. So this plot here is your GRB duration, your hardness ratio. These 2 kind of clouds here are your long duration GRBs and your short duration GRBs. You can see that 211211 sits smack in the middle of the long GRB population. But very surprisingly, what we discovered when we followed it up with Gemini was this very red counterpart that fades a lot like this known Kilonova AT 2017 GFO. So you can see here, these squares up at the top especially are the near infrared band. The dashed line is 17 GFO, and you can see that it really looks like this one known Kilonova. So what we take away from this event is that, okay, now we have a larger population of kilonovae, we can start to see some diversity in them, but also diversity in the GRBs that come from neutron star mergers. So with this discovery and the 2 decades of archival observations that we have, I was really interested in looking at what do kilonovae and how diverse are they across both classes. And then are there trends between GRB and kilonova properties? So we went to uniformly model 8 kilonovae, all found following GRBs, including 170817, although of course that's not your typical GRB. So we did this using MOSFET, which of course was built here at Harvard, led by Ashley Villar and James Gilad. The model that we use takes into account geometry. And so it's a 3-component model in which each of these different components is parameterized by a different ejecta opacity and kind of ties into a different ejecta mechanism. So there's lots in this project that I would love to talk about, but I'm only going to highlight the red ejecta mass here, which is linked to dynamically ejected material from tidal interactions of the 2 neutron stars. And as they in-spiral in towards each other, this material is stripped off. Okay, so this is our sample of events. These are 8 kilonovae. This is just 2 different afterglow models that we used. Of course, right in the middle, you have 170817. I will never lie to you, none of these light curves are anywhere near as beautiful as 170817's, but we can still get a lot of good information about kilonovae and their diversity from studying them. So from our multi-component kilonova modeling, so these are different just plots of the ejecta masses and then the posteriors for each of the events in our sample. So this is the first time that this has been done for multi-component modeling. We produced medians, which are these black lines, and then the 68% confidence interval. 170817's kilonova is labeled with a red star. And so we see 170817 is really an average kilonova. The other conclusion I'll highlight is that we looked at the different component ejecta masses relative to the gamma ray properties. And so especially in these top panels here, we potentially see a trend between the red ejecta mass and the total ejecta mass with gamma ray energy, both corrected for jet opening angle and not. Whew. And so our conclusion kind of from this is that this is maybe suggesting if you have a greater amount of this red tidal dynamical ejecta, that a progenitor for those long-lived gamma ray signals could be asymmetric compact object binary progenitors. So I'll just leave my conclusions up here, but I want to say first, this work was not done in isolation. I want to thank my advisor, Wen Fei, and a large team of people, and thank you so much for having me.
Probably ignorance on my part, but the discovery of neutron star, black hole, neutron star collisions is a very promising environment for making the R process, which hadn't previously been known. Is there a kind of overall mathematical sum here? Like, do these actually produce enough to account for what we see in the R process?
Yeah, I wish I had there's a great plot from Kenta Hodakazaka where I think the biggest uncertainty is not actually the ejective mass of the kilonova. It's more the rate of the neutron star mergers, which is pretty uncertain in the universe. I think LIGO is getting better constraints on it, and we have some constraints from short GRBs. But when we think about the total R process in the Milky Way, for instance, and how we were able to produce that, the biggest uncertainty to reconcile with that is the neutron star merger rate.
Thank you. Any other questions? Well, thank you. You're admirably clear.
Next slide.
Okay, so now we're going to hear from our own Charlie Lada on molecular clouds on Andromeda.
Okay, there it is. Well, I'm very happy to be able to come here today and share with the ITC community some very, what I think are intriguing and impressive observations of giant molecular clouds in the Andromeda galaxy. These observations were taken with this, by this small team that you see here with our very own SMA. And I'm now going to review for you the results of a large SMA program that was designed to acquire deep and resolved simultaneous measurements of both dust and gas in over 100 individual GMCs in M31. So I'm only going to be talking about 12 and 13 CO emission today because of the time constraints. So I'll get right to it. And here are the sort of the basic results of our survey. We looked at 80 SMA fields across the disk of M31. And for me, one of the most fantastic results that came out was the incredibly high singleton noise spectra in 12CO and 13CO that we were able to obtain for all of the 162 resolved GMCs that were in our sample. And a big surprise for me, again, was that about 70% of the clouds that we resolved and detected had very simple single component line profiles that could be more than adequately fit by single Gaussian functions, as you can see by the red lines, at least 4 of the 5 examples that I showed here. And it's this group of clouds that I'll be talking about mostly in the rest of the presentation. But to give you an idea of the quality of the data that we have, I'm showing you here some SMA images of the dust continuum emission in a couple GMCs in M31, along with 12 and 13 CO contours that you see there overlaid. And to put this in some perspective, this is what the Orion A and B molecular clouds would look like in 2-to-1 emission if in Andromeda and sampled with the same configuration of the SMT and with the same sensitivity that we had for our survey. Ditto here for the scaled Planck observations of Orion A and B. Now, to give you an idea how deep we actually went, I find this to be illuminating. This is a HST image of one of our GMCs where we have the 12 CO contours plotted on it. And you can see when you look at the extinction and the 12 CO contours that we're really tracing molecular clouds out to the very edges. We're getting, for at least most of the sample, very robust measurements of masses and sizes. And about half the sample, over 80 of these clouds, we trace the molecular emission down at the 3 sigma level to about 1 magnitude of visual extinction equivalently, and even below. This is getting very close to the actual atomic molecular phase transition in this galaxy, which is around a half a magnitude of extinction. We can learn a lot about the molecular clouds and their natures by examining Larson's relations for these objects. Now, Larson's relations, there are 3 of them, as many of you probably know. They include 2 scaling relations, one between mass and size, another between velocity dispersion and size, and the virial relation. And these relations have been used for over 4 decades to really probe the natures of molecular clouds, both in this galaxy and others. So let's look at the first relation that I'll consider is there a mass-size relation in the GMCs of M31? And here I plot the masses versus sizes of both 12 and 13 CO, and you can see, yes, there is definitely a highly correlated mass-size relation. There are solid lines there of the least squares fit to the data. The parameters of the fits are also shown, and also along the dashed lines with like 25, 50, and 100. Those are lines of constant surface density in solar masses per square parsec units. As impressive as these fits are and these relations are, however, you notice there's also a fairly large scatter. And it's this scatter that I'm particularly interested in because encoded in the scatter is actually more physical information about the nature of the clouds in this relation than you get from any other parameters, say, for example, like the slope. So what is the origin of observed scatter? To really understand that, you have to understand how we define clouds. So on this particular study, we define GMCs by a fixed outer surface boundary, sigma 0, which we set equal to the 3 sigma noise level in each of our images. Now, over a 4-year survey at any observatory, you're not going to get the exact same sensitivity in all your observations. And there are a number of fields that don't come close to what we really wanted to have. And so that introduces a spread in the sigma zeros, which in turn introduces a spread in the mass-size relation. So what I want to know is how much of the scatter can be accounted for by that. So I'll start with a simple hypothesis, and that is, like in the Milky Way, the clouds in Andromeda on small scales have power law PDFs for their surface densities or column densities. If that's the case, then when an observer defines a surface density like we do, that surface density is directly proportional to the boundary surface surface density that you adopt, and the constant of proportionality is solely dependent on the index of the power law and power law PDF. So this led to a simple experiment. We divided our sample into 3 groups, with each characterized by a separate adopted surface density, the values you see here, and we required that to be in any one of these 3 groups, a cloud had to be within 10% of that, have an outer boundary within 10% of the boundary listed there. So we then constructed mass-size relations for those 3 groups. You see them here on the left. And if you look at the table, which is the parameters of the least squares fit that you also see in the diagram, from both the diagram and the table, you see some interesting results. First, The slopes of the relations are invariant to the outer boundary that was used in defining the clouds, as you would hope. The dispersion is actually remarkably small. It's a factor of 3 index smaller than we get for the aggregate relation. And indeed, it's about the same level that we get when we look at local clouds in this way. In addition, as you look at the prediction, the surface density does actually increase with the boundary surface surface density, and the coefficient is indeed, as predicted, pretty constant. Because of that, we can actually then turn it around and calculate what the power law of the PDF would have to be for the clouds and their internal PDFs. And we got a number of 3.7, which doesn't mean very much to you unless I compare it to something. This is what we find for local molecular clouds from extinction observations. So I conclude from that M31 GMCs may have power law and PDFs on scales smaller than we're observing that are very similar to the Milky Way. But what does all this have to do with the initial question, what causes the scatter? You can see here right away from comparing these two things that almost all the entire scatter comes from the boundaries that you define for molecular clouds in this relation. Now, to give us some more context, this is comparing our 80 most sensitive observations of M31 in line with the mass-size relation compared to what we get for local molecular clouds within a kiloparsec of the sun. Least squares fits, the parameters are shown there. And then also I've put the average surface densities that we calculate for both samples. And you can see, just looking at that, the molecular clouds in M31 are indistinguishable from those of the local interstellar medium. Now, what about the second relation? Is there a line with size relation? Well, here I plot the line with, or velocity dispersions versus size in both 12 and 13 CO emission for the M31 clouds. And then you can fit least squares fits to these, and you can see that it looks like there might be a relation if you look at the parameters there in the red, where the slope is 0.39 for the C12 CO. That's basically the same answer Larson got 40 years ago for local clouds. The correlation, though, is weak, and if you look at the correlation coefficient, it's less than a half, so it's kind of a modest correlation at most. If you look at 12 CO, 13 CO, you find that it's even less correlated than 12 CO with a slope of a quarter and a really paltry correlation coefficient of 0.3. So from that I conclude, yes, in 12 CO there probably is a line with size relation, but it's a weak one. 13 CO, in my opinion, is, I can't justify that there's a real line with size relation. Even if I'm wrong about that, the line with size relation seems to be scale dependent in M31 clouds. Finally, if you look at the virial nature of the clouds, you can see on the left I've plotted the virial masses versus the luminous masses. And the giant molecular clouds that we see in 12 CO do not appear very virialized. In fact, surprisingly, only 40% of them actually even appear bound. About 60% of the sample is unbound. But when you look at a 13 CO, which really represents the cores of these clouds, or many of these clouds, you see a very different situation. They all fall on the virial line, more or less, and 94% of them are bound. But even though most of the GMCs we see in 12 CO are not bound, the question comes, could they be pressure confined by, say, the midplane pressure of the galaxy or the pressure of the surrounding interstellar medium? So here I plot a Keto diagram, as I call it, which is a very useful tool because it shows you the theoretical trajectories of clouds virialized with surface pressures, ranging from P of k to 0 here, all the way to P of k of 10 to the 6. And what you note is that the actual sources in M31 span a very wide range of required pressures for confinement, not anything like a single pressure to confine them, but, and it's over 2 orders of magnitude in extent. And this is just really implausible for any kind of simple confining pressure from the galaxy, except if you consider that I've color-coded these observations by the value of the sigma 0 that we determine for each of the clouds in our survey. And if you just look at clouds where we go down to the very edges of the clouds, you see that this required pressure collapses, and it's actually, moreover, in the exact range that we'd expect for the midplane pressure of the disk of M31. Now, these other clouds to the right of that, require much more or additional sources of pressure if they were to remain in pressure equilibrium. But you have to understand that these clouds have to not only balance the pressure of the ISM, but they have to balance the weight of their envelopes that we are missing because of the way we define the clouds due to our noise limitations. And moreover, if you look at the way this trend is, you find that you require a lot more additional pressure as you change the surface density boundary to higher and higher values. So to look at this finally a little closer, it's just showing you what on the keto diagram, the traces of individual molecular clouds look like. And what's really interesting is you notice that they're kind of parallel to the virial equilibrium pressureless curve, and that means they're crossing many, many isobars. And they're doing it in such a way that we're seeing pressure gradients where the pressure is increasing as you go inward. And on the right, I've just taken one of the clouds out of that sample and actually plotted its pressure gradient, radial pressure gradient. You see it's a very well-behaved function. It's fit by a nice power law, high correlation coefficient, and a slope of minus 1.5, but isn't too different from what you would expect from the Lane-Emden equation for a hydrostatic object in pressure equilibrium, meaning that it's very likely that most of these clouds, although they appear bound in the simple potential energy versus kinetic energy analysis, are very likely pressure-bound objects in hydrostatic equilibrium. And I just should point out this is very similar to what Eric Keto showed 2 weeks ago at the ITC lunch for analysis he did of local molecular clouds. So with that, let me close. And let me say, if there's anything I want you to take away from this talk, it's that now with instruments like the SMA, we're observing clouds of the same kind of degree or same fidelity in a galaxy like M31 as we are in the Milky Way, and that the M31 clouds are almost distinguishable in many aspects to the clouds that we see locally. Yet M31, as you may know, is a very different kind of galaxy. It's had a very different history. So,
So, I think I got the answer to this question, but I'm going to come forward again anyway. Broadly speaking, there's no kind of significant driving difference between molecular clouds and Andromeda and molecular clouds and Kilonova. Is that what you're saying?
yeah, that's right. I think on these scales, on the scales of individual clouds.
So Andromeda is a better place to study them because you're not stuck in the middle of the plane.
What's that?
You're not stuck in the middle of the plane. You can actually.
Yeah, that's, a big advantage. The reason we see these nice simple profiles is in part because the galaxy's inclined enough that that we, unlike the Milky Way, we're not looking through at zero inclination. So the Milky Way is really, really compromised by the fact that when any direction you look at, you get overlapping clouds and things. It makes it very hard to do this analysis.
Any other questions? Tony, please.
So one big difference between M31 and the Milky Way is that the center of the Milky Way is full of molecular material.
Yeah.
The center of M31 is not. So I was just going to ask, what is the radius of your innermost GMC that you're studying?
Well, I could show you that.
Roughly speaking.
It's actually pretty close. It's right at the edge of the bar. You know the central bar in M31? I think it's on here. You can see those red things in the middle. That's where, that's as close as we get. And you can just barely see the little bar in the middle. So I can't remember. That's like 5 or so kiloparsecs, maybe. I don't remember exactly. And those are the ones that are red because for some reason, we didn't detect 13CO in those clouds.
Any more questions? Yes.
What is the scatter and line of size relation? It also depends on boundary or the transit
Well,
radius.
What's that?
Scatter and the line with size relation. What's it? The scatter.
Oh, the line with size relation. Yeah, we looked at that by seeing how it varied with the choice of the outer boundary, and there's no difference. You get the same line with size relation, even though you might expect because the R is changing and everything, but no, we saw no difference in that relation due to the systematics.
Are there any trends with concentric radius?
No, we also looked at these things as a function of galactic central gradients, and we didn't see any trends, although you have to realize that because M31, most of the clouds are in a 10 kiloparsec ring, we're kind of heavily weighted to that, so.
Okay, well, before we make all the speakers again, just checking the Eric Keeper's website is on here. And Eric, of course, is very generously a supporter of the food for these meetings. I should have mentioned earlier. So let's thank Charlie and all the other three speakers.
Yeah, they did, but some of them are bigger ones. Mine was sort of space.